welcome back. It's been a while. So today I'm just gonna tackle this question on quantum mechanics. It's an infinite square well problem. So I think I would just give a brief on what is an infinite square well. Infinite square well is a type of area, I would say, where this it looks like a box. Okay, it just looks like a box like this, and at the boundaries there is an infinite potential. So in this infinite potential, when the particle or the at quantum state the particle enters, so it becomes bounded, and between in between this region the particle acts as a free particle because there is no potential here, but at the boundaries there are infinite potential, so potential tends to infinity, so it becomes bounded. So we just consider this area for the wave function. So it is an infinite square well problem, and it's a pretty simple problem. We have been given the conditions, so we are considering a wave function of dependent on x and the infinite square well. So it is from the square well extends from 0 to x, and on the left hand side of 0 there is infinite, on the right hand side of x there is infinite potential. Okay, so we just need to first find the normalization of this function. So we need to find the normalization of this function. It is said that n is equal to 1 state. So for n is equal to 1 state, we get the wave function comes out to be this wave function, which is dependent on, which is given as sine n pi x a is given as 1 x is equal to sine pi, so n becomes 1 x, which can be written also as sine pi x a. Okay, and then we have the wave function, which is the infinite square well function, which is given as this 1x. Here a is the amplitude constant. Okay, so a sine this I am doing something, this is written as sine pi x a. So we have to normalize this function for the sum. So we normalize this, we normalize. So normalization, we all know that it is like this: wave function conjugate wave function is equal to 1. If it is not equal to 1, then it is not normalized. Okay, so we normalize this wave function whole square. Okay, wave function here, this one, and we just do this a square sine square pi x a, and it will come out to be a by 2 x is equal to 1. So here, from here we can find 1 is equal to 2 by a whole square, and which comes out a is 2 by a. We normalize this function to find out a. Okay, because we need to prepare for the next one. We need to find this as a time derivative, so it depends on time also. So x, which is a function of x and t, gives us this one, a x and t, which is given by as we know this one as summation of pi n is equal to 1 from 0 Cn e to the power I En En which is given, t by h cut, okay, and the wave function that is given to us, this one. Okay, so we just for the second one we just write here like this. So for n1 state, n is equal to 1 state, we consider this as 1, okay, because there is no summation, this is a one state, we are considering only one state, so this one just becomes 1. So we just write e to the power I en t by h cut phi x naught, which can also be written as I en t h cut and can be written as root over 2 by a sine pi x by a. I think I should have gone into the details of integration of this part, but I think it is a pretty simple integration, because you just take out this one, this does not depend, you just take out and you just integrate over this one, you just substitute this factors, so you consider this as u and you just continue on. It is not a very hard integration, okay. Secondly, and then we just get x t for n1 state, okay, for n1, we are not considering n2. If we consider n1, n2, n3, we get this summation, it will not equal to 1, it will not be, so we just get this function, okay. And this is the wave function for number 2's answer, okay. For number 3 we need to find the h cap. Now h cap is given as the conjugate h cut square twice m h cut square twice m of the function's double derivative of this function of x that we just found out here. So we need, this is the basically we are considering the energy of the particle in the square well, okay. We are considering the average energy, we are not getting only one particle, so it is the average, we need to take the average value. So this is the average value of the energy of the particles. This is now question number the question number 1's part number 3, so we need to find this one. And here it will take some while, but you think you know there this double derivative with respect to x, we just gonna get, I'm just gonna write it directly because it's not gonna be too much hassle if I just go on writing everything, because it's just gonna come out as it will be like pi square, then it would come as pi square and twice m a square. So this will be our answer for the part number 3, this will be the answer for our part number 2, and the this will be normalized. We just normalize this to find the amplitude constant, that's all. And now how did this come? It's gonna take 1 or 2 pages to completely solve this one. It's gonna take 1 pages, so I seriously don't want to do it because it's gonna take some time. Next time I will try to do more sums, and if you think that I should do every sum step by step, please leave a comment and I will be sure to reach out in the next video. Thank you and have a good day.